Hello, thank you for being here. I'm Yonsei, who is advised by Professor Lee. It is a great honor to be able to speak to you today. This afternoon, I'll be talking about organic single-ion conductors for lithium metal batteries. As you can see, I'm gonna divide it into three parts. To start with, I'll introduce lithium metal batteries, including why they are used and an issue we faced in using them. Then I wanna explain the research ion-rectifying polymers and covalent organic framework for lithium metal batteries. After that, I'm gonna describe the summary and perspective. Why do we use lithium metal batteries? Lithium is the most promising anode for obtaining high energy density due to its high specific capacity and low reduction potential. However, it has an issue of low Coulombic efficiency and volumetric expansion due to lithium dendrite growth, are a serious challenge that contribute to safety issue and cyclability. Here you can see during charge process, lithium ion can migrate from electrolyte to lithium metal anode. Then the concentration of lithium ions at the electrode-electrolyte interface reaches zero, that is called sense time. In order to elevate concentration polarization, decreasing anion transverse number is required for suppressing dendrite formation. In this section, I plan to give some brief insight into how important single-ion conductor has become in battery system. Quite simply, lithium ions are engaged in redox reaction, while anion remain inactive. For dual ion conductor, the freely mobile anion tend to cause unwanted interfacial side reaction electrode. However, single ion conductor can mitigate concentration gradient. That means suppression of dendrite formation. So we focus on how to control anion mobility. Then I want to classify two types of single ion conductors. Although inorganic single ion conductor have high lithium ion conductivity at room temperature, but they have poor contact with electrode. However, organic single ion conductors has been investigated owing to their fossil processability and close interfacial contact with electrode. So I will focus on organic single ion conductors. As shown in this slide, I divided research into two categories, ion-rectifying polymers and covalent organic framework. Firstly, let's focus on ion-rectifying polymers that allow fossil lithium-ion transport. In this part, I'd like to say something about polymeric porous sponge host that can lead to higher local concentration of lithium ions than network solution. So the interfacial electric double layer, due to the strong lithium ion affinity, promotes the electrokinetic surface conduction and electroosmosis. In other words, the electrokinetic pumping feature could accelerate the lithium ion transport in the host and therefore improve the lithium ion self-concentrating kinetic. Next, they demonstrated a new class of printable solid electrode interface as a simple and scalable strategy for lithium metal batteries. Both ion conductivity and transverse number tend to increase with the DA-DMMA TFSI content, which is quasi single ion conduction material. So to better understand high lithium transverse number, FDR analysis was conducted. The PFC's anion could be electrostatically trapped by the positive charged ammonium groups of DA-DMMA, indicating the electroporosis-driven ion-rectifying effect. Next, I'll talk about Covalent organic framework compared to polymers, porous crystalline materials such as cough and muff has been pioneered as an appealing alternative due to their directional ion conduction pathway through the ordered pore and versatile structure design. And next, they demonstrate for the first time cation moiety incorporated into skeleton cough material can easily split the ion pair of the lithium salt, boost the concentration of freely mobile lithium ions, and thus improve the lithium ion conductivity in cough-based lithium ion conductor like this. Notably, the cation cough effectively screen the Coulombic interaction due to greater polarizability compared to cough with neutral framework. Another cough is lithium sulfonated cough as a new class of solvent-free single lithium-ion conductor. So benefiting from well-designed directional ion channel, the high number density of lithium ions and covalent tetrad anion groups that cough exhibit ion conductivity 2.7 10⁻⁵ Siemens per centimeter with high transference number of 0.9 at room temperature without any kind of sorbent salt and organic sorbent. So unusual ion transference phenomenon of that cough allow reversible lithium plating stripping lithium on lithium metal electrode, demonstrating its potential use for lithium metal batteries. To summarize, two different design concepts are proposed for the organic single-ion conductors with a focus on immobilizing an ion-rectifying polymer and covalent organic framework. So these organic single-ion conductors allow the high cation transference number, contributing to reversible stripping plating of lithium electrode, along with elevating the concern on a dendrite growth. When it comes to perspective, organic single-ion conductor promising option for lithium metal batteries. In order for organic single-ion conductors to be considered suitable candidate for replacing conventional electrolyte, the energy density and technical challenge must be resolved. So firstly, the design of highly fast ion conductor should consider interfacial compatibility with electrode. And then in addition, research emphasis should be placed on the development of processability for lithium metal batteries. Currently, lithium-free anodes are being explored as well. Finally, machine learning has recently emerged as a promising modern approach to determine the state of charge and remaining useful life of battery without experiment. So we envision that organic single-ion conductor described herein hold promise as an effective and versatile material platform to move lithium metal batteries closer to commercialization. Okay, that's end my talk, and thank you for your time.